So, if you recall our discussions from the first couple of weeks, to make a feedback system, we needed to take the difference between the input and the feedback quantity. In this case, I will assume them to be voltages, and pass the difference through an integrator. Okay. And the output of the integrator is the output of the feedback system, and a fraction of it gets fed back. Okay. That's the idea. So, what we need is a differencing block plus integration. Okay. So, if we have a block that does these two functions, we can use that in a feedback system and make a feedback amplifier out of it. And the combination of these two is what is an Opamp. Okay. An Opamp is trying to do this. It's trying to get you the difference and the integrated version of that difference. We also saw that there are a number of non-idealities associated with it. So, ideally we would want the frequency response to be that of an ideal integrator. Okay. This is the frequency response between V in minus VSB and V out. Okay. This is the magnitude. In reality, at low frequencies, the gain is not infinity, and at high frequencies, the slope is more than minus 20 dB per decade. Okay. That is more negative than minus 20 dB per decade. But largely, it is this thing that we are interested in. That's what gives us the feedback control action. Okay. So, we would like to make something that does this. We know that reality of life doesn't let us do that, so at least we would like to do something of this sort. Okay. So, how would we go about doing it? Now, we know how to make amplifiers, and if you look at most of our amplifiers, they take a voltage in and give a voltage output, but what is happening internally is that they convert the voltage to current, and that current is in turn converted to a voltage using a load resistor. Okay. That's how we have the common source amplifier, for instance. This gives us voltage to current conversion. An incremental current at the gate source, incremental voltage at the gate source gets converted to an incremental drain current, and that is passed through a load which will give you I to V. So, finally, you have an amplifier with a voltage input and voltage output. Now, a differential pair is nothing but a common source amplifier, some differential version of that. So, that also does the same thing. This part of the circuit, the tail current source and the transistor give you a current that is proportional to the difference voltage. Okay. So, this part gives you V2 I, and that I can be passed through a resistor to get you a voltage output. Okay. So, we can represent this as an amplifier, but a more precise representation is that of a transconductor followed by a load resistor. So, the amplifiers we have are of this type. So, this is the symbol for a transconductor, and if we use a differential pair, we can take the difference between two voltages. What we need is an Opamp that gives V out as a function of V1 and V2. Okay. In fact, we would like V out by V1 minus V2 to be omega u by s in the ideal case. Okay. So let's say we have a transconductor that responds to difference between V1 and V2. That means that it tends to push out a current Gm times V1 minus V2 when V1 and V2 are applied to its inputs. And we want to get a response like this. That is, we want the response of an integrator. How will we get this? We know that a capacitor integrates the current to give you an output voltage. And here we have a current, so if we push this into a capacitor, okay, what is the transfer function? If this is V0, V0 by V1 minus V2 as a function of frequency, what is it? What is it? Gm by SC. Okay. So what is the unity gain frequency of this integrator? It's Gm by C, right? It's the proportionality constant that multiplies 1 by S. That's the unity gain frequency. So if we have a transconductor, we can get the block that we need for our feedback system by loading it with a capacitor. Okay. So this is what we have so far. I mean, in terms of this, we know we want this from our basic analysis, and from our knowledge of circuits, we have this one. Okay. To get the integrator from the transconductor, we can simply load it with a capacitor. Of course, there are more and less complicated versions of the transconductor. We'll see why we need it afterwards. But this is one way of making an Opamp or an integrator that takes the difference between two inputs. Okay. Now, initially while designing feedback systems using op-amps, I had said that we have some non-idealities in op-amps, that is the finite DC gain, and there is a second pole and probably a third pole and all of that stuff. And I had not really given any reason for it, I said it will be there. Now we can see why it is there. Okay. So let's say we start off with this idea that we have a transconductor, we have something that converts voltage to a current, and we can load that with a capacitor. To get our integrator. So ideally the response looks like this, where the unity gain frequency is Gm by C. Okay. This is the magnitude of V0 by V1 minus V2. Why would this circuit have a finite DC gain? What would make the circuit have a finite DC gain? Finite power supply. Why would that do that? We are talking about small signal incremental gain here. What's that? How much charge the capacitor can hold? Okay, what is the gain of this at DC? A constant current will flow through the capacitor and it will become infinite. So if it can't flow through the capacitor, you will have a finite DC gain. Okay. So all our transconductors also have a finite output resistance. If you have an R across this, what will be the DC gain? Gm times R. Okay. So if you have a resistance in parallel with the capacitor for whatever reason, it could be a load that you connect, or it could be the output resistance of the transconductor. In either of these cases, you will have a finite DC gain, not an infinite DC gain. And what will be the response of this, frequency response of this block? V0 by V1 minus V2, what is it? Gm by 1 plus SCR. Yeah. So the current is proportional to Gm, and then we have two things in parallel. This is SC plus G. Okay. And we can write this in a couple of forms. This is the DC gain divided by 1 plus S divided by G by C, okay, or S times CR. This can also be written in another form which I have used earlier, 1 by okay plus, we had put things in this form earlier, right? We had 1 divided by S by omega u plus 1 by A naught. So if A naught is infinity, this goes away and it becomes an ideal integrator. So the DC gain is GMR, and R is any resistance that you connect as a load or any output resistance that the transconductor has. Okay. So we clearly see that we cannot make infinite DC gain because every transconductor that we have seen so far has a finite output resistance. Okay. Is this okay? So we try to make this. We know that we have transconductors, we also have capacitors, so we can make an integrator this way, but we'll always end up with some resistance. Okay. So this is why we'll have a finite DC gain. So we'll design some Opamp and see that this in fact is true. And what would make it do this? Huh? The input? The input pole. So essentially, if GM itself has a frequency dependence, okay, between the input and output, you will have something of the sort. If there is some frequency dependence inside the transconductor. Okay. So in fact, you can make it without this also. We'll see. Right. So it is possible to have something like this, predominantly a first order response. But most of the good op amps that we will design will have some poles inside the GM, and because of that you will have something of this sort. Okay. So this is just to connect what we have now to what we discussed long back, so that we can go and design the op amp. Okay. So for this block we will use the differential pair that we analyzed in the previous class. We did large signal analysis and we just thought of it as a new circuit and we went and analyzed that thing. Okay. So now I will discuss some techniques that we use in particular for analyzing differential circuits. The differential pair that we derived look like this. We had only resistances on one side, the resistance on one side, but to complete the symmetry we put it on the other side also. Okay. And we also said that it is convenient to analyze if we split the signal into differential and common mode signals. Okay. And we can define the output from either side to ground or between the two corresponding nodes. Okay. I am assuming that there is perfect matching, so M1 and M2 are perfectly identical. So in general we will have a class of circuits like this which have two identical halves that are connected at some common node. Okay. So these are fully differential circuits. So if this is some circuit A, this is also exactly the same circuit. Okay. So let's say this is node 1 of the circuit A and this is node 2. This is node 2 and node 1. So some nodes may be connected in common, maybe some nodes are separate. Okay. In our case, the sources of the transistors are connected to a common point, the drains are kept separate. But we can clearly think of this as two identical halves which are connected at some nodes. That we can do easily by thinking of the current source as a parallel connection of two identical current sources of half the value. Okay, now you can clearly see that this part of the circuit and this are identical. The source happens to be connected, okay, and the drains are not connected. Now, you can, of course, keep every transistor and every component in the circuit and analyze the circuit. You will get the right answer. But there is a simplification that you can make. Okay. So let me consider two identical halves. And let's say this, I'll call the input. It can be anything, but and this is some common node. I have taken only one place, but it could be that there are many corresponding nodes that are connected together. Okay, you have two halves of the circuit. You have two identical circuits. It's not just that one node of this circuit is connected to corresponding node of the other circuit. It could be many nodes. Like many nodes here could be connected to corresponding nodes on the other side. So this is common, and each one has some ground reference. This is the input, and I'll call this the output. Again, there may not be an explicit output, it's whatever node is there in the circuit. Now let's say first of all I excite this with a common mode of 0. This is Vd by 2, this is minus Vd by 2. Okay, the circuits are identical and the excitations are equal in magnitude and opposite in phase. So what can you say about these two voltages, and what can you say about this voltage? Let me call it VO1, VO2, and then this may be Vx. Okay. What can you say about VO1, VO2 and Vx? The only thing you know is that the two circuits are identical and they are driven by antisymmetric inputs. What is the value of Vx? Why? Doesn't change. Why? How will you prove that it is 0? What's that? Yeah, how do you say that? You use superposition. So first the two circuits are identical. So first I'll apply Vd by 2 to this side and 0 to the other side. Okay. What will I get here? I don't know, but I'll just call it some Vx1. Okay. Now I can apply 0 and Vd by 2 to the other side. What will I get at this point? Vx1. Because the circuits are identical, I still get Vx1. Now if I apply minus Vd by 2, I'll get minus Vx1. Okay. So the sum of the two is 0. So the common nodes that are connected between the two halves of the circuit will be at 0 volts. For a linear circuit, it will be always 0. For nonlinear circuits, it will be 0 in an incremental sense. Okay. For small increments, it will be 0. Right. That example we saw here, the tail node is one thing that is common to the two halves. We have connected it together. If you do large signal analysis, you see that the slope of that voltage with respect to the input voltage is 0. Okay. So it is 0 in an incremental sense. So what will be VO1 and VO2? Or at least how will they be related to each other? Negative of one another. So again, we can use superposition to see that. So I apply Vd by 2 and 0. I don't know what I'll get, but let me call it just VO1A and VO2A. Okay. And if I apply 0 and Vd by 2, just the two voltages will be interchanged. Okay. I'll get VO2A here and VO1A here, because again the two circuits are identical. And if I make this minus Vd by 2, this will become negative, this will become negative. When I apply both simultaneously, I'll get VO1A minus VO2A here and VO2A minus VO1A here. So the two outputs will always be antisymmetric if the excitation is antisymmetric and the circuits are exactly symmetric. Okay. So these are two things that we can figure out about any circuit that can be split up as two half circuits that are exactly identical, and when you drive them with antisymmetric inputs, the nodes that are not connected to each other, the corresponding nodes on each side will go equally and oppositely. Okay. And if there is a common node, if corresponding nodes are connected together, they will not change at all. They will be at 0 volts. And for a nonlinear circuit, it is 0 in the incremental sense. That is, for small increments, it will be 0. Okay. So this is one thing that simplifies the analysis. Fully differential meaning every part of the circuit is symmetric. If you excite them with antisymmetric inputs, that antisymmetric input is also known as purely differential. Okay. That means that the common mode component is 0. Okay. When you do this, the corresponding nodes in each half are equal and opposite. Rather, I should say corresponding, the voltages at corresponding nodes in each half are equal and opposite, and this also holds for currents. If you look at corresponding branches between the two halves, if one of them has an upward current of some magnitude, the other one will have a downward current of the same magnitude. So it is not just voltages, it's currents and voltages. And if you have common nodes between the two, okay. And similarly, if you have a branch that is common to the two, that is, for instance, this branch, I can draw this as something like this, right? So you can think of this particular branch as common to the two circuits. So the incremental current in this branch will be 0. Okay. So this is true of any circuit that is made up of two identical half circuit and excited antisymmetrically. So what about it? This is true. So how does it help us? So we know that when we excite it antisymmetrically, this will be at 0 volts. And if two voltages are identical in a circuit, you can actually connect them together. You can do this in most cases. The only place you can't do it is at the input of an Opamp. Okay, input of an ideal Opamp. So we can connect this to ground. Then we can analyze only one half of the circuit, because we know that the other half behaves exactly identically, because it's the same circuit. Okay. We want to get the individual voltages, that is fine, because we analyze one half of the circuit and we know that on the other half we will get the same magnitude and opposite phase. Okay. So this idea, this concept, the circuit that you get by grounding the common node is known as the differential half circuit. So this will let you analyze a simpler circuit, right? Basically you analyze half of the circuit. So this implies that This is known as differential half circuit. There is a different half circuit for the common mode. Okay. What I meant was, if you have an ideal op-amp, these two voltages are always equal, right? So, for instance, I make some circuit like this. If it's an ideal op-amp, these two voltages are equal. But if I short these two and analyze it, I'll get something completely different. I cannot do that. Okay. It's actually something weird. I don't fully understand it, but it doesn't work. That's all I know. I mean, you can very easily see that it won't give you the right answer, right? If you short the inputs. The current, the idea with this amplifier is the current in this resistor should flow through the other one. But if you short it, it will flow here. Okay. What's that? No, this has nothing to do with differential circuits, right? In any circuit, if you find two voltages at identical potentials, you can connect them together. That's what you learn in circuit theory, right? Node voltage, the equations will not change, isn't it? Any circuit. So I have let me maybe redraw this. I have, let's say, R1, R2, and I excite it with some voltage. I get V times R2 by R1 plus R2. Okay. I have C2, C1, so I excite this. I get, what do I get here? V times C2 by C1 plus C2. Okay. So I connect these and it remains the same. Is this okay? Have you seen a circuit like this? So you make of course, I am assuming that R2 by R1 plus R2 is C2 by C1 plus C2. Under these conditions, the ratio between these two is independent of frequency. Where will you use this circuit? So this is what is used in an oscilloscope. Okay. This is actually a very useful circuit. You have an oscilloscope, and the input, if you remember what was written on it, it said something like 1 megohm in parallel with some 13 picofarad or something. I mean, many picofarads. But more than that, you connect a long cable to it. You connect 1 meter of cable, it probably has approximately 100 picofarads of capacitance. Okay. Now, essentially, you are driving a very large resistance and a large capacitance of the order of, let's say, 100 picofarads. Okay. And you are familiar with the times 10 mode of the oscilloscope, X10. Sometimes to reduce the loading on the circuit, now this 100 picofarad will load this circuit a lot, perhaps. So to reduce the loading, or maybe an alternatively to measure high voltages, your oscilloscope measures up to 20 volts, you want to measure up to 200 volts, you can connect 9 megohm resistors in series. But this voltage division works only for DC, right? For AC, what happens is, because of this capacitor, you will have a low pass filter between this input and the oscilloscope input. So you also connect a capacitor between these two. Okay. And then you adjust the value of the capacitor until the ratios are equal. How many of you have used the oscilloscope in this mode? Nobody? So, again, if you remember the oscilloscope, there is a square wave output from the oscilloscope. Okay, this is an aside, but there's some interesting information anyway. Why do you think the square wave output is there from the oscilloscope? It's to test this. You put in a square wave. To a circuit like this. What will you get at the output? What will you get? Square wave. No, I didn't say that the ratios are the same. The ratios may not be the same. What happens if the ratios are not the same? C2 by C1 plus C2? Okay. You apply a step of 1 volt. What will be the output voltage after a long time? Huh? Oh, after a long time, what will be the output? R2 by R1 plus R2. Immediately at the jump, what will be the output? C2 by C1 plus C2. Right? The resistor, no current flows through the resistor when you apply a step. All of it flows through the capacitor. So it could be C2 by C1. I mean, it could be above this or it could be below this. So depending on the ratio, you will see something like this or something like this. Okay. And when the two ratios are equal, you will see a flat one. So you apply the square wave to the probe, you measure this oscilloscope output with the probe, and you look at it and you adjust it until you see a flat trace. Otherwise, if the capacitor ratio is larger, you will see something like this. If it is smaller, you see something like this. Okay. That's why it's used. So anyway, this is all distracted from what we were discussing initially, that if you have two node voltages to be identical, you can connect them together without affecting the circuit. And you can, there's a very easy way to verify this. You write some circuit equations, the network equations in a general format, like KCL equation in terms of the node voltages. And if two node voltages are the same, you can connect them together. No extra current flows through that. You'll be able to formally prove that this is the case. Okay. Yeah. Yeah, so there is something wrong with it, but I don't know exactly what is wrong. But it is a fact that the two voltages are identical, right? So, yeah, that's true. I mean, if you short it, then there is no feedback and that's why it doesn't work. But exactly where the reasoning breaks down, or maybe there is something, I should write the circuit equations and see something is inconsistent when you run through the formal argument. That must be the case, but I haven't done it yet. Okay. So, for our purpose to derive the differential half circuit, it's enough to know that the common node will be at 0 volts. So, we will actually tie it to 0 volts. Then we have two separate circuits. Every common node, it could be that there are many and all of them will be at 0. Okay. You tie all of them to 0 volts. You have two separate circuits. Now you analyze only one half of it. Okay. And you can get all your results for the other half from this half. Is this okay? So the next thing is, of course, in reality you don't only have differential inputs, you also have common mode inputs. What will you do in that case? So the circuit has a number of nodes internally, but I will just show as one node, N1, okay. And this time around, I don't have antisymmetric inputs, I have identical inputs to the two sides. Okay. So that is known as a purely common mode input. That is, there is no difference between the two, there is only, you apply identical voltages to the two inputs. So what will happen to, this is not grounded of course. What will happen to Vx, VO1, VO2, all of these things? What can you say about Vx? Huh? It will be twice of Vx. You can't say anything, it depends on the topology. What can you say about VO1 and VO2? They will be the same? Yeah, because they are identical circuits. Again, I run through this quickly. I have VCM and 0, I get something here, VO1A and VO2A, and I have 0 and VCM, the two will be interchanged. So I get VO2A added here and VO1A added here if I apply both simultaneously. Okay? And that is true of all of the nodes, internal nodes also. Each corresponding node will be at the same potential. Okay? It could have 100 nodes there, but you look at the corresponding nodes between the two halves, in the two halves, they will be at the same potential. So, does this simplify your analysis in any way? Or is it as complicated as analyzing the full circuit? We can't say anything about Vx. The common node, it will have some potential. At least I don't see how we can say anything about Vx. It depends on the circuit. The only thing I can say in this case is that the corresponding nodes in the two halves will be at the same potential. So what will you do? So again we use the same idea. If two nodes are at the same potential, we connect them together. Okay? So I connect the two outputs together, I connect these two together, and every corresponding node I connect together in the two halves. So what happens? It's simply like folding the circuit on top of itself. Essentially I have shorted all of the corresponding nodes. I'll show you exactly what I mean by folding. If you have a symmetrical circuit with identical inputs or common mode inputs, then corresponding node voltages and it also applies to branch currents. The two halves are identical. Okay? So you connect corresponding nodes together. So what is the simplification you got from this? What's the big deal? Has it simplified the circuit? We have half the nodes in the circuit. So clearly if you, and we generally, as you know, don't analyze circuits with more than two nodes. So now we'll have only one node and it's very easy. Okay. So number of nodes reduces by 2x. So it is useful for analysis, but it's not only that, as we'll see. Because what happens is we have some single-ended circuits and we have differential versions of it. It's also more to get insight into what is happening and so on. So when you reduce it to half circuits, it will become similar to or identical to some circuit that you already know. I'm assuming that you know single-ended circuits, you don't yet know differential circuits. So when you connect up these half circuits together, it will become identical to some single-ended circuit that you know. So then you can do the analysis easily, but it's not only for analysis, it's also for you to get an insight into what is happening. So we can work out the example. We already have a sample differential circuit. Okay. I will make it, and the exact symmetry in the circuit is very important. I mean, if you have identical transistors here, but different loads, this is not true. Okay. It's only true for exactly identical circuits. And I will replace the tail current source with some MOSFET. We have to do it at some point. Okay. And it has some other aspect ratio, W0 by L0. And call this M0, M1. And M2. Okay. and I apply, in general I would have applied VCM plus VD by 2 here and VCM minus VD by 2 here, and I will define my output to be between these two. Okay. It can be again I can define it to be either from one side to ground or between these two. And I want to get V out divided by VD and V out divided by VCM. How will I go about doing it? All small signal analysis, so linearity holds. Finally, I am interested in V out divided by VD and V out divided by VCM. Okay. So what is the result if you short the two? Huh? Okay, let's do the analysis and see. How will I calculate V out by VD? Yeah, but the output is defined between two sides. Huh? No, that is, how are you saying all this? See, what I do is, first of all, so first I will apply only differential signals when I want to calculate V out by VD. In this case, I already know that this is something, whatever it is, okay. If this is V drain, this is minus V drain, okay. And what is V out in terms of VD? Minus 2 VD, okay. It's V out is defined from this side positive to this side negative. That's why I want to go through the whole sequence of steps so that you also get the sign correctly, not just the magnitude. V out is the difference between minus VD and VD. So this is minus 2 VD, okay. So now I have everything in terms of variables that are on one side, okay. So what do? This I know is to be grounded, okay. So I will analyze this circuit. And this was anyway grounded for incremental purposes. And here I get VD. And here I have, maybe I should have used a different sign, V lowercase d divided by 2. So what's the answer? What is V uppercase D? What's the drain voltage? Huh? It is minus GM RL. Actually, to be more precise, it will be minus GM by GL plus GDS times VD by 2. And I know what V out is. So V out is minus 2 times this whole thing. So it is plus GM by GL plus GDS times VD. Okay. So it turns out that the gain between the differential input and differential output is also GM by GL plus GDS. Okay. And this whole thing became easy because the differential half circuit is our common source amplifier, which we have analyzed so many times. Okay. So we took a long time to get here, but now all of the differential circuits we analyze will be of this sort. Okay, it will be some differential version of common source, common gate or common drain amplifier. So we already have done the analysis ad nauseum for the single-ended circuits. We can go through the differential circuits more easily. So it also gives you an insight that it should be the same as common source amplifier. Right? Which one? No, I can take anything I want. It doesn't matter. I'll take something on this side and something on the other side. No. So his question is that I took plus VD uppercase D on the left side and minus V uppercase D on the right side. So I'll do this. Okay. So what is this voltage in the half circuit? Minus VD, because I am analyzing this part of the circuit. Okay, and minus VD is this much. And how much is V out in terms of VD? Plus 2 VD. Okay, so I get the same answer. Right? I reduce V out to a difference between two voltages defined with respect to ground, because in the half circuit I don't have these two nodes, I have only one side. Okay, but I know that the corresponding nodes on each side go equally and oppositely. Okay, that's why I defined the node with respect to ground, define the voltage with respect to ground, because this V out is not there in the half circuit. I have only half of the circuit, so I define everything, all the variables with respect to ground, then I analyze it, and if my voltage happens to be something like this, I can take the appropriate difference. And by the way, first of all, it doesn't have to be between corresponding nodes. I mean, for some bizarre reason, I could maybe split the resistor in two. Okay, the circuit is still symmetric, and my V out is between these two. What will I do in that case? So let's say, for whatever reason, I want to find out the difference between these two voltages, and the circuit is symmetrical. This is R1, this is R2, and that goes to VDD. How will I do this? I'll define two voltages here. Maybe I'll call this V1, call this V2, okay, and this will be minus V2 and minus V1 under purely differential excitation. And what is V out in that case? Minus V2 minus V1. So I use the differential half circuit to calculate V1 and V2 in terms of VD. Then I can calculate V out in terms of VD also. Okay. So that's why it's good to define something with respect to ground and then move on. Of course, you do it a couple of times, you can do it without thinking and without explicitly doing all of this. Okay. So the differential pair gives a differential gain of Gm by GL plus GDS. Okay. If the input is applied between M1 and M2, with M1 being positive, the gate of M1 being positive and gate of M2 being negative, the output will be positive if you take the gate of drain of M2 as positive. Okay, it's on the opposite side. So there is inversion between the gate of M1 and the drain of M1, and there is no inversion between the gate of M1 and the drain of M2. Okay, and this is a pretty common thing with differential circuits. I want to calculate V out by VCM. What do I do? What is? It will be 0. So again, I do the same thing, go through the systematic procedure. Of course, after a while, you can see the answer right away. So I apply identical inputs to the two sides. Actually, this doesn't require any thought at all, right? My output is between these 2 points. Let me call this VD. If this is VD, under common mode excitation, this will also be VD. And the difference between those two will be 0. So I don't have to do any analysis. Okay? So let's say I am interested in, this is the output taken differentially. I want the output common mode. That is, I want the sum of these two voltages, the average of these two voltages. Okay? Then what do I do? So I just analyze this circuit and calculate VD divided by VCM. Okay? What will I analyze? Let's say I am interested in VD divided by VCM. Yeah, what is it? So let's say this is the differential pair. Okay. and I will define the positive output node here and the negative output node here. Okay. So, what is the differential output? I define that to be VOP minus VON. What is the common mode output? I define that to be the average of the two. Okay. So, in general, I would want the transfer function between the output differential and common mode and the input differential and common mode. So, basically, I want all these four ratios: V out D by VD, V out D by VCM, V out CM by VD, and V out CM by VCM. So, the ratio of output differential voltage to input differential and common mode voltages, and ratio of output common mode voltage to input differential and common mode voltages. Okay. This we already evaluated. It is the gain of the common source amplifier. This is 0 because of symmetry in the circuit. What about this? That is also 0 because of symmetry in the circuit. You can easily prove to yourself that that's the case. So, finally, I am interested in the output common mode divided by input common mode. How much is that? That is what I calculate using the common mode half circuit, right? I apply a common mode input and I look at the output, and that's what I get. So, for instance, if I okay, and again I will define the two drain voltages to be VD. If one side is VD, the other side is VD because of symmetry. Okay, and what is the output common mode voltage in terms of VD? It's VD itself, right? It's the average of VD and VD. Okay, so I need to calculate VD divided by VCM. So I have these two transistors which are identical, W by L, W by L, and this has an aspect ratio W naught by L naught. What is the common mode equivalent circuit for this? Common mode equivalent half circuit. I have to short the corresponding nodes. So I short these two. So I will get RL in parallel with RL. So this is RL by 2. I have a single transistor whose width is twice that of each of the transistors, and this is W naught by L naught. Okay, and this is VD. Assume that each of these transistors is modeled by GM and GDS. That is, let's say this is GM1, GDS1, and this is GM0, GDS0. So before the next class, please calculate the gain between the input common mode and the output common mode. Okay. So we use the half circuit. When you do the half circuit, what happens is, if you have resistances, they tend to become half, because they will become half because you connect them in parallel. The MOSFET width will double, because for every MOSFET on this side, there will be some other MOSFET, there will be another MOSFET on the other side. We connect the corresponding nodes in parallel, so the two MOSFETs will appear in parallel. Okay, so the width will double. If you have resistances, the resistance will half, or conductance will double, and capacitances will double, and so on. Okay, so that's the general idea.